Hi everyone. So this is all about assignment 53, which is going to be the derivatives of log and exponential functions. We're also going to put logarithmic differentiation here. But before we get to that, I actually want to go back to the last section where we were talking about inverse trig functions, and I kind of wanted to look at this little yellow box, because often these little yellow boxes have really interesting information in them. So here the little box says derivative of inverse functions. If f is differentiable at every point on an interval, from a to b, and this is very important, and the derivative of f with respect to x does not equal 0. If the derivative of this equals 0, not going to work. Derivatives of inverse functions has to meet these two prerequisites. F is differentiable on that interval that you're looking at, and the derivative of f is never equal to 0. Now think about that. Here's my f prime sign chart. Derivative is never equal to 0. So either I get a plus, which means that this function is always increasing, or I get a minus, in which case this f function is always decreasing. And if I think about, always increasing or always decreasing, what I notice is while I might be going from concave down to concave up and so on, or even just this linear thing, I am now, though, thinking about, well, what's the implication of this derivative never being equal to 0? Sure, I'm monotonic, but also I can't have this happening. Why do I care about that? Well, I know there's a slope of 0 there. I know I'm going from positive slopes to negative slopes. And this says the derivative can never be equal to 0. Because if the derivative is equal to 0, then I can have this max, and then this can happen. Does this have, oh look, I failed the horizontal line test. So no inverse possible. So in order to have a differentiable inverse, remember you need two things. F is differentiable on an interval, and 2, df dx is never equal to 0. If you get both of these preconditions, then what do you know? You know that f has an inverse and f prime exists for, now be careful about this, it's not exists on that interval, it's the function evaluated on that interval. And that's just a quick way of saying, when we were thinking about inverse functions back in pre-cal, remember how we had to switch the inputs and outputs. So this is me saying this derivative will exist, f inverse prime exists for all the outputs of this original function. All right, so what am I getting at with this? Well, I'm getting at, we need to have a conversation about this problem, because this problem is something that I've actually seen show up on the AP exam, and I would like you to feel confident and comfortable if it happens to show up while you're taking the AP exam. All right, so I'm looking now at this function. F of x equals cosine x plus 3x. All right? And the first thing I'm asked to do is show that f has a differentiable inverse. Show that f has a differentiable inverse. Well, if I take the derivative of this, I'm going to get the derivative of cosine is negative sine, and the derivative of 3x is 3. Okay, so good. That's nice. Now, remember the prerequisites for differentiable inverse? Differentiable inverse if the derivative exists everywhere, because I don't have an interval here. Yes, I can graph that, and this graph goes on forever, so I'm willing to believe that this derivative has no discontinuities in it. Good. And then what was the second thing? The second thing was that f prime is never equal to 0. Well, think about this graph for a moment. It's a negative sign graph, but it's been shifted up 3 places. And so our graph looks like this, and this is 0, 3, and this is pi over 2, 4, and this is pi 3, and this is 3 pi over 2, 2, and over here we have 2 pi 3. See? Look, what do you see? This derivative is never equal to 0. So, since the derivative exists, is continuous, like there's no discontinuities here, this derivative is definitely existing for all real numbers, and the derivative is never equal to 0. We see that. Here's the derivative graph. It never crosses there. Then we know that f has a differentiable inverse, which means that f inverse exists and f inverse is differentiable. That's what we know about that, right? Wait, there's more. If f of x equals cosine x plus 3x, first question says find f of 1 and f, oh, sorry. Am I reading the right one? No, I'm not. F of 0. There we go. Find f of 0, and what was the other thing? Find f prime of 0. Okay, so f of 0 just means plugging a 0 into each of these. It's the cosine of 0. And 3 times 0 is 0, and so I know f of 0 is 1. In order to find f prime, I'm going to have to take the derivative of this. Well, we already did. We know that f prime is minus sine x plus 3. If I plug a 0 in here, the sine of 0 is 0, plus 3 is 3. Excellent. Now is when the fun starts. I want to know what f inverse of 1 is equal to. This is actually a pre-cal question, maybe even algebra 2. So, if this point exists on f, what point must exist on f prime? Remember, to make an inverse function, I'm sorry, this isn't prime, it's inverse. In order to make an inverse function, I'm going to flip those inputs and outputs. Look. So if this point exists on f, then this point, flip the x's and y's, must exist on f inverse. Okay? All right. So now let's take a look at f inverse prime of 1. What's that going to be? Well, let's think about that graphically. We know that logs and exponentials are inverses of each other. This point is 0, 1. This point is 1, 0. This one has a horizontal asymptote. This one has a vertical asymptote because we switched. What did we switch? We switched y equals 0. We switched the x's and y's, and now we've got x equals 0. So at this point, I see a slope. What's the relationship between that slope and this slope? It's very interesting. And by the way, if this point, for example, was 1, 2, then I know on this graph there's a point called 2, 1. I can find the slope here, but what would be true about the slope here? At the inverse point on the inverse function. Some students want to say, oh, well, if this is, a slope of positive 1, then over here I'm going to have a slope of negative 1. And that's not true because both of these are positive slopes. Okay, so if I know the slope here to be 2, slope here equals 2, the slope here turns out to be 1/2. They're not opposite reciprocals of each other. They're just reciprocals of each other. I wonder if we can say why. Well, remember how slope was rise over run? And we thought about that as a change in y over a change in x? Yeah? And so remember, when we're talking about inverse functions, we're flipping x's and y's. A change in x over a change in y. See, it's the reciprocal of this one. So whatever the slope is on the original function at the original point, the slope on the inverse function at the inverse point is the reciprocal of that slope. I'm going to say that again. It may not be enough times. Here's my original function. Here's my original point. Here's the slope at that original point. On the inverse function, at the inverse point, and what I mean by is we switched the x's and y's, the slope at that point is the reciprocal of the slope on the original function at the original point, because when we make an inverse, we switch the x's and y's. I have seen this problem show up on the AP exam, I think 3 times in the last few years. So I think it's probably worth spending a little time doing it, and I strongly encourage you to take a look at problem 28 on page 175 for those of you with a textbook in your hands. Yeah, that's not going away. You will, of course, forget it, and I will remind you of it painfully once or twice more this year before you take the AP exam. And at some point, you should probably then draw a big highlighter box around this truth and acknowledge it thusly. Okay, now let's move on to the topic for today, which is all about the derivatives of exponentials and logs. So I want to start off with something like y equals e to the x. There's my function, and I want to take the derivative. Well, remember on that microscope worksheet where it turned out that in fact all the slope values you got at -1, 0, and 1 turned out to be the same as the y values on the original e to the x function? Well, there we go. It is its own derivative. And if you don't believe me, why don't you type this into y1 and n deriv into y2, and then go over to your table feature and see what happens when you plug different x values into your calculator. You'll be getting exactly the same answer because e to the x's derivative is e to the x. Now, what about something like f of x equals e to the 3x? Well, the derivative there is just going to be e to the stuff, because e to the is e to the's derivative, times, don't forget to take the derivative of the inside function. So my derivative is itself times the derivative of the inside function. Or e to the stuff, the derivative of e to the stuff is going to be e to the stuff times derivative of stuff. So how about f of x equals e to the 2x minus 5? Will you show me what that derivative is? Did you get f prime of x is going to be e to the 2x minus 5 times 2? Because remember, the derivative of e to the stuff is e to stuff times derivative of that stuff. Good. And that seems all very reasonable and straightforward. And then Mr. Euclid does this. Y equals e to the x squared minus 5x plus 6. Please find y prime. Okay. Let's see what you got. Excellent. Did you say e to the x squared minus 5x plus 6? Because the derivative of e to the stuff is e to the stuff times, what was it? The derivative of stuff, 2x minus 5. Fabulous. How about if y equals, don't hate me, 100 over 1 plus e to the 3 minus x. Hey, look at that. That's a logistic curve. And Kukla's asking me to take the derivative of it. Sure am. I think I'm going to flip the bottom up. Like that. Don't try and apply this exponent to these places. I'll have to find my Poole Newton. So, what's the derivative? I'm going to bring down that negative 1. 1 plus e to the 3 minus x to the negative 2, right? You bring it down, you subtract 1, times the derivative of the inside. The derivative of 1 is 0. The derivative of e to the stuff is e to the stuff times the derivative of stuff. Derivative of 3 is 0, and I can't tell you how many people forget the derivative of negative x is negative 1. Wow, look at that. No, don't simplify it. I mean, you can. You'll certainly see it simplified on multiple choice, and I've never seen this show up anywhere else but multiple choice or the calculator portion of the test. But here, I guess I could tidy that up. I could move these to the bottom and have this on top. So it's not that horrible to simplify, but we've got too much to do, so let's move on. How about y equals e to the x squared times sine of 3x. Please find y prime. Pause the video, come back when you're done. All right, welcome back. So this is clearly I'm sorry, I didn't mean to do that. This is a product rule problem. Function times a function. All right, so derivative of this, e to the x squared times the derivative of the inside, 2x, times that. And that seems like maybe it should be enough, but no, because we're doing product rule. We did the derivative of this times this. Now we need the derivative of that times that. So we're going to have e to the x squared times the derivative of sine is cosine. Leave the inside alone. And don't forget to come back and take the derivative of 3x. Yes, you could factor this out, but it's not going to get me very far. So I don't particularly think it's worth it, but I'll certainly show you because it's not an unreasonable test question. And that's about as far as I can go. Okay, so there's y prime in its simplified form. Okay, so what next? Well, next I'd like to take a look at y equals ln of x. I want to know how to do the derivative here. Well, so here's the thing. I have no clue. I haven't seen this before. What is this ln? How am I supposed to take its derivative? I want to actually use a little algebra here. I want to exponentiate both sides of this equation with e. Why? Because remember ln is really log base e. E raised to the power of log base e. What happens to those things? They cancel, and I'm left with that. So this is that. Okay. So on the left side, I have e to the y. On the right side, I have x. Now let's take a derivative here. The derivative of e to the is e to the times the derivative of that inside thing with respect to x equals the derivative of x is 1. Since we're doing implicit differentiation, you want to get dy dx by itself, so you're going to divide both sides by e to the y. Okay, so dy dx equals 1 over e to the y. Now, this is good. This is good. What's e to the y equal to? One over x. So the derivative of ln of x is 1 over x. Let's write that down clear. If y equals ln of x, y prime is 1 over x. Okay? Derivative of ln of stuff is 1 over stuff. So if I had y equals ln of u, and u is some function of x, then y prime is 1 over stuff times the derivative of stuff. Okay? So be mindful of chain rule here. Okay, so with that in mind, will you please say what the derivative of the ln of 5x is? What would y prime be? Isn't that interesting? So we know the derivative of ln of stuff is 1 over stuff. Don't forget to come back and take the derivative of stuff. Damn! That's the same derivative that ln of x had. Yeah, but this time we're doing ln of 5x. Huh. How about y equals the ln of 3x squared? Well, this derivative is going to be 1 over stuff times the derivative of stuff. And look, there's some canceling we can do. What happens with that canceling? This x cancels one of those. I got a 2 over x. Well, that's really interesting, because I got that 1 over x with this 2. Where's that 2 coming from? I don't see a 2 here. Yes, I'm just going to leave it out there. Instead of going further down that road, let's keep going. 10 over x. So y prime, give it a try. Come back when you're done. I'm interested to know something about what you did in this problem. Okay, so the derivative of ln of stuff is 1 over stuff, ew, times the derivative of stuff. Now, I don't want to use quotient rule here. I'm doing 10x to the minus 1. So my derivative is negative 10x to the minus 2. Then fraction over fraction, I don't like it. So I'm thinking about this as 1 divided by this fraction. I'm going to do the flip and multiply. Times negative 10x to the minus 2. Behold. And here, what can we do with those? When I'm multiplying and the bases are the same, I add the exponents. Don't lose that. Damn! There's the 1 over x again. This time we have a negative 1. Okay. I think you need to do some more of these. How about this one? Y equals ln of x. Please find the derivative of this. You really should be practicing these. You need so much practice in your derivatives, I promise. I mean, half of second semester depends on you remembering all these derivatives. Right. So, y prime. I didn't say it wouldn't be funny looking. 1 over stuff, right? The derivative of ln of stuff, here's my stuff, is 1 over stuff times the derivative of stuff. There we go. So we get 1 over x ln of x. Great. And this last one, y equals the ln of sine x. Actually, I want that. All right, we'll just do it your way. But, remember, ln won't eat a negative, and sine will poop out negatives. So if we have those absolute value bars, then we don't have to worry about sine pooping out any negatives. All right, so y prime, what do you think? 1 over sine, right, because 1 over stuff, times the derivative of stuff. So you're telling me that cotangent is the derivative of this? How the hell did that happen? But we saw it. There it is. Yeah, plain old cotangent is the derivative of this ln of sine. I just find those sort of things really, really interesting. All right, so we did an exponential, we did a log. I'd like to come back to exponentials now and look at something in a more general form. A to the x, okay? A is some number. I believe we want a to be a positive number, and I think we want a not to be equal to 1. Yeah, because if a is equal to 1, then we could get that 1 to infinity case, and I don't want to talk about indeterminate forms right now. So, with the understanding that a is a positive number not equal to 1, then this is what I would think to do. I would say I would really like to get this down. So I'm going to take the ln of both sides, and then I'll use that power rule. Remember, it's the log power rule, not the derivative power rule. So we have ln of y equals x ln of a. Now, this is really, really, really important. This is a variable. This is not a variable. This is some number. Remember, a to the x. So maybe it's 2 to the x, maybe it's 3 to the x, maybe it's 1/4 to the x. These are my a values. So when I do ln of a, I'm doing ln of these bases. This is ln of some number. This is not a variable. This is a constant. So I might, if I had done 2 to the x, have x ln of 2 here. ln of 2 is a number. But we haven't taken the derivative yet. So let's go and take the derivative. The derivative of ln of y is 1 over stuff times the derivative of stuff equals, what's the derivative of x times a constant? X times a constant. What's the derivative of x times a constant? I don't use product rule for this, so don't use product rule here. The derivative of x times a constant is the constant times the derivative of x. So the derivative of x times a constant is just going to be the constant times the derivative of x, which is 1, and so I get ln of a. Remember here we're trying to solve for dy dx, so multiply both sides by y. dy dx equals y ln of a. And what was y originally? A to the x ln of a. This is my derivative of a to the x. So let's see if we can summarize that a little bit. If y equals a to the x, then y prime was a to the x ln of a. Okay? Now let's think about this. Y equals e to the x. Y prime then is going to be e to the x times ln of the base. Right? That's the base. That's ln of a. What's ln of e? 1. And that's why this thing that we've been doing with e to the works, is because here's the general form, and yes, there is an ln of a, except in this case ln of e is 1, and so we don't really see it. But when we have something like y equals 2 to the x, y prime is going to be, itself times the ln of the base. And our base here is 2, so we want ln of 2. Okay? So what happens if I have something like y equals 5 to the x squared plus 3x, and I want y prime? Well, the derivative of a to the stuff is going to be a to the stuff times ln of a times, oh my god, you didn't forget chain rule, did you? 2x plus, hey, there's a derivative over here. Okay, again, if we're talking about y equals a to the x, y prime is itself times ln of the base. But what if we have stuff up here, right? What if this is u, and u is a function of x? Well, then don't you forget du dx over here. Chain rule still lives. You've got to multiply by the derivative of that inside function. This is not the derivative of inside anything. This is a constant that is part of the derivative of a to the power. All right,